Somewhere off the coast of southern Africa, where the Atlantic and Indian Oceans crash into each other with the kind of violence that breaks ships in half, sailors used to whisper about a vessel that could never make port, a ship caught between worlds, not alive, not sunk, just sailing, forever. The Flying Dutchman. You've heard the name, you've seen it in movies, in paintings, in every pirate story that needs a ghost ship to raise the stakes. But here's what almost nobody talks about. The Flying Dutchman wasn't pulled from thin air. The legend is built on something real. Real ships, real engineering, real captains who pushed Dutch shipbuilding to its absolute limit and paid the price for it. And when you look at what the Dutch were actually building in the 1600s, the hulls and the rigging and the insane ambition behind these vessels, the ghost story starts to make a different kind of sense. Because the real ships behind the legend were, in many ways, more extraordinary than the myth. To understand any of this, you need to picture a map, not a modern one. A 17th century Dutch maritime chart, hand-drawn on vellum, showing the route from Amsterdam down the western coast of Africa, around the Cape of Good Hope, and east toward Batavia. That route stretched roughly 15,000 nautical miles. 6 to 8 months if the weather cooperated, and the weather almost never cooperated. Now zoom into the bottom of Africa. The Cape of Good Hope. Portuguese sailors originally called it the Cape of Storms, and they weren't being dramatic. This is the point where two massive ocean systems collide. The cold Benguela current flowing north from Antarctica meets the warm Agulhas current pushing south from the Indian Ocean. When those two systems meet, especially during the southern hemisphere's winter, the result is some of the most violent and unpredictable sea conditions anywhere on the planet. Waves routinely reach 15 meters. Freak waves, what modern oceanographers call rogue waves, can exceed 30 meters. Winds shift from calm to hurricane force in less than an hour, and the currents themselves can run at speeds that no 17th century ship could fight against if caught head-on. This is the stretch of ocean where the Flying Dutchman legend was born, and the ships that attempted this passage were products of the most advanced maritime engineering program in the world at the time. The Dutch Republic's shipbuilding industry, the Dutch Golden Age, running roughly from the 1580s through the 1670s, wasn't just about paintings and tulip speculation. It was industrial shipbuilding on a scale nobody had ever attempted. At the peak of Dutch maritime power, the shipyards of Amsterdam, Rotterdam, Zaandam, and Enkhuizen were producing between 500 and 1,000 vessels per year. To put that in perspective, that's more ships per year than the entire rest of Europe combined. The backbone of this fleet was a vessel called the Fluit, and the Flute is one of the most underappreciated engineering achievements in history. Designed around 1595 in the town of Hoorn, the Fluit was built for one purpose: cargo capacity per crew member. That sounds dry, but it was revolutionary. Before the Fluit, European merchant ships were essentially repurposed warships. They carried cannons. They had wide decks for fighting. They needed enormous crews to man the guns and handle the rigging. The Fluit threw all of that away. The hull was shaped like a pear, wide and round at the waterline to maximize cargo space, then tapering sharply above to create a narrow deck. That narrow deck wasn't a design flaw. It was a tax dodge. In the 1500s, several major European ports charged tolls based on deck area. A narrow deck meant lower tolls. So the Dutch built ships that were enormously fat below the waterline and skinny above it, carrying more cargo while paying less to move it. The dimensions were striking. A typical Fluit ran about 80 feet long and could carry between 200 and 300 tons of cargo. Before we go any further, I need to stop for a second, because what I've been showing you in these videos only scratches the surface. And I realized at some point that the full picture, the actual pirate code, word for word, the real punishment records, the exact treasure division shares, the ports that secretly funded them, it doesn't fit in a video. I put it all into one document, the Black Flag Codex. It's linked below, And the QR code is on your screen. Now, let's keep going. But it needed a crew of only 12 to 15 men. Compare that to an English merchant vessel of the same era, which might carry the same tonnage but require a crew of 30 or more. The Dutch were moving the same goods with half the labor cost. How did they manage this? The rigging. Flute rigging was designed for simplicity. The masts were tall, but the sail plan was straightforward, using a combination of square sails on the foremast and mainmast, with a latent sail on the mizzenmast. More importantly, the Dutch pioneered the use of blocks and pulleys that allowed a smaller crew to handle larger sails. The mechanical advantage built into the rigging system meant that 2 men could do the work of 5 on a comparable English ship. The construction method was equally innovative. Dutch shipyards were the first in Europe to use wind-powered sawmills for cutting timber. They standardized hull components so parts could be pre-cut and assembled quickly. A fluid could be built in 3 to 4 months, compared to the year or more required for a custom-built warship in an English or Spanish yard. But here's where the Flying Dutchman story really begins. The fluid was perfect for European coastal trade. It was not designed for the kind of voyage that the Dutch East India Company, the VOC, needed it to make. The VOC, founded in 1602, was arguably the first multinational corporation in history. It had its own military, its own legal system, and the authority to wage war, negotiate treaties, and colonize territory. At its peak, the VOC employed roughly 50,000 people and operated a fleet of nearly 5,000 ships. And the VOC needed ships that could do something no European trading vessel had ever done reliably: sail from Amsterdam to Southeast Asia and back, carrying hundreds of tons of spices, silk, porcelain, and other high-value cargo across 30,000 nautical miles of open ocean. The round trip took 18 months to 2 years. The fluid couldn't handle it. The hull was too lightly built for the massive swells of the southern Atlantic. The narrow deck left no room for the defensive cannons needed to fight off pirates and rival navies. And the rigging, optimized for the relatively calm North Sea, couldn't survive the sustained gale force winds of the Cape Passage. So the VOC engineers did something remarkable. They took the core principles of the fluid, the efficiency, the crew-to-cargo ratio, the standardized construction, and built an entirely new class of vessel around them. The East Indiaman, the VOC East Indiaman, was a hybrid. Part merchant vessel, part warship, part floating warehouse. The hull was wider and deeper than the fluid, with heavier planking and additional structural ribs to withstand the punishment of deep ocean swells. A typical large Indiaman ran 150 to 160 feet long, nearly twice the length of a fluid, with a beam of 40 feet and a displacement of 600 to 1,200 tons. The keel was critical. Dutch shipwrights used oak for the keel, sometimes a single massive timber running the entire length of the ship, reinforced with iron bolts and additional bracing at the bow and stern. The keel had to be strong enough to absorb the shock of waves that could exert thousands of pounds of force per square foot against the hull. Above the keel, the ribs were spaced more closely than in a flute, typically 12 to 14 inches apart, compared to 18 to 20 inches in a coastal vessel. Each rib was made from naturally curved oak, selected specifically for the angle it needed to hold. Shipwrights would spend weeks in the forests of Germany and Scandinavia, choosing individual trees whose trunks grew at the right curve for a specific position in the hull. The planking was applied using a technique called carvel construction. Unlike the overlapping clinker-built hulls of Northern European tradition, carvel planking laid each board edge to edge with the seams caulked using oakum, which is tarred rope fiber, and sealed with hot pitch. This created a smooth hull surface that moved more efficiently through water and was easier to repair at sea. Between the outer planking and the inner lining, many East Indiamen incorporated a layer of sacrificial wood, typically softer pine, designed to be eaten by shipworms without compromising the structural oak beneath it. Shipworm, specifically Teredo nivalis, was one of the deadliest enemies of any wooden vessel. These mollusks could bore through an oak hull in a matter of months in tropical waters. The sacrificial layer bought time. Later in the 17th century, the Dutch began experimenting with lead sheathing on the underwater portions of the hull. Thin sheets of lead were nailed over the planking to create a barrier against both shipworm and the marine growth that would accumulate on a hull during a long voyage. A fouled hull could reduce a ship's speed by 30 to 40%, which on a Cape passage could mean the difference between making it through a weather window and getting caught in a storm. The masting and rigging of an East Indiaman represented another leap in complexity. A fully rigged ship carried 3 masts plus a bowsprit. The mainmast on a large Indiaman could stand 100 feet above the waterline, made from a single pine trunk reinforced with iron bands. When a single trunk long enough couldn't be found, masts were assembled from multiple timbers using a technique called fishing, where overlapping sections were bound together with iron hoops and rope woolding. Each mast carried multiple yards, the horizontal spars from which sails were hung. A fully rigged East Indiaman could spread between 10,000 and 15,000 square feet of canvas. The running rigging involved miles of hemp cordage. Literally, a large Indiaman carried between 20 and 30 miles of rope. And the rope itself was an engineering product. Dutch rope walks were among the largest industrial structures in 17th century Europe. The rope walk at the Amsterdam VOC yard stretched over 1,000 feet. The quality of the rope directly determined whether a ship could survive a Cape storm. A single line failure at the wrong moment could bring down a mast, and a lost mast in heavy seas meant a ship that couldn't steer and could easily founder. Now imagine pushing all of this engineering through the Cape of Good Hope. The passage typically required sailing south from the equator along the African coast, picking up the southeast trade winds, then swinging east around the Cape and into the Indian Ocean. The approach to the Cape itself was where everything got dangerous. The continental shelf south of Africa creates a zone where the water depth drops rapidly, from 200 meters to over 3,000 meters in a very short distance. When the Agulhas current, flowing southwest at speeds up to 5 knots, encounters swells from the opposite direction, the wave energy gets compressed. Waves that are 8 meters in open water can double in height as they hit the current. The result is a zone of standing waves, cross seas, and chaotic wave interference that has sunk ships for as long as humans have been sailing around that corner of the world. Dutch captains learned to time their Cape passages for the southern hemisphere's summer, roughly November through March, when conditions were slightly less murderous. But slightly less murderous still meant regular encounters with 50-knot winds and 10-meter swells, and the passage could take weeks, with ships unable to round the Cape against headwinds and forced to tack back and forth, sometimes losing ground for days at a time. This is where the legend takes root. A ship stuck off the Cape, unable to make progress, battered by storms, its crew dying of scurvy and exhaustion, would have been a familiar nightmare to any Dutch sailor. And occasionally, a ship would simply vanish. No wreckage, no survivors, just gone. Between 1,602 and 1,795, the VOC lost approximately 150 ships. Not all of them sank at the Cape, but enough did that the passage had an almost mythological reputation among Dutch crews. And here's where the specific legend of the Flying Dutchman starts to crystallize. The earliest written version of the legend appears in a 1790 book called Travels in Various Parts of Europe, Asia, and Africa by John MacDonald. In his account, the crew of a ship near the Cape spotted another vessel in distress during a terrible storm. They tried to approach, but the ship seemed to always stay the same distance away, no matter how they adjusted course. Eventually, they concluded it was a ghost ship, doomed to sail the Cape forever, unable to make port. But the version that stuck, the one that became the definitive Flying Dutchman story, involves a specific captain. His name varies depending on the source. Some accounts call him Hendrik van der Decken, Others name him Bernard Fokke. Bernard Fokke is the more interesting candidate because he was a real person. Fokke was a VOC captain in the mid-1600s who was famous for making the Amsterdam to Batavia run in an impossibly short time. Contemporary accounts suggest he completed the voyage in roughly 3 months and 4 days, which was considered borderline supernatural. Normal transit times ranged from 6 to 9 months. Fokke did it in half that. How? This is where engineering and legend overlap. Fokke was known for pushing his ships harder than any other captain. He carried more sail in higher winds. He made his crew work in conditions that other captains would consider suicidal. And he may have understood something about ocean currents and wind patterns that his contemporaries didn't. The Roaring Forties. Between 40 and 50 degrees south latitude, the prevailing westerly winds blow with almost uninterrupted force across the Southern Ocean. There's almost no land to slow them down. A ship that dropped far enough south could catch these winds and essentially ride them east at speeds that were impossible on the standard, more northerly route. The problem was that dropping south into the Roaring Forties meant entering some of the roughest seas on Earth. The wave fetch, the uninterrupted distance over which wind can push waves, extends thousands of miles in the Southern Ocean. Waves build and build without anything to break them. A ship in the Roaring Forties was a ship in constant danger of being overwhelmed. Fokke apparently did it anyway. And when he arrived in Batavia impossibly fast, people couldn't explain it. The conclusion among superstitious sailors was obvious. Stop for a second. What you just heard about the pirate code is the part that rewrites everything you thought you knew. But it only lands when you see the actual shares, the exact fractions written into the Articles of Agreement, the punishments, the port records, the names of the men who funded them from government offices. It's all in the Black Flag Codex, linked in the description. 5 seconds, grab it now, because what comes next builds directly on it. Link is below. QR code is on your screen. He had made a deal with the devil. And when Fokke eventually disappeared at sea, which he did, the legend was complete. He was the captain condemned to sail forever, the Flying Dutchman. But let's strip away the supernatural and look at what Fokke was actually doing with his ship. Because the engineering decisions involved in riding the Roaring Forties in a 17th century wooden vessel are genuinely extraordinary. First, the hull had to be strong enough to take continuous beam sea conditions. Beam seas are waves hitting the ship from the side, and they're the most dangerous orientation because they induce rolling. A ship in the Roaring Forties running east before the wind would take quartering seas, waves hitting from the stern quarter, which create a combined rolling and pitching motion that puts enormous stress on the hull. The structural weakness of any wooden ship is the connection between the keel and the frames. In heavy seas, the hull works, meaning it flexes. The bow rises on a wave while the stern is in a trough, and the entire ship bends like a plank laid across a gap. This is called hogging. The reverse, where the middle of the ship rises while the bow and stern drop, is called sagging. Repeated cycles of hogging and sagging can fatigue the hull connections to the point of failure. VOC shipwrights address this with a system of internal bracing called riders and stringers. Riders were heavy transverse timbers bolted across the hull frames at key stress points. Stringers were longitudinal timbers running fore to aft inside the hull, tying the frames together and distributing the bending forces over a larger area. The combination created a semi-rigid internal skeleton that could absorb the flexing without allowing the hull to work itself apart. The masting was equally critical. In the Roaring Forties, wind speeds regularly exceeded 40 knots, with gusts to 60 or more. At those speeds, the force on a square sail is enormous. The pressure on a single topsail in a 50-knot gust could exceed 10 tons. That force had to be transmitted from the sail through the yard and mast, through the mast step, the socket at the base of the mast, and into the keel. If any component in that chain failed, the mast came down, and a dismasted ship in the Southern Ocean was essentially a death sentence. With no ability to steer or make headway, The vessel would be rolled beam on to the waves and eventually capsized or broken apart. This is why Dutch captains carried spare spars, hundreds of fathoms of extra rope, spare blocks and deedies, and the tools needed for emergency rigging repairs at sea. The crew included specialist riggers and carpenters whose entire job was keeping the masting and rigging functional under extreme conditions. Fokke's secret was probably a combination of three factors. He chose the right season. He understood the current patterns well enough to stay in the strongest part of the westerly flow, and he drove his ship harder than anyone else, accepting a level of risk that other captains considered insane. But the legend needed one more ingredient: the ghost sightings. Throughout the 18th and 19th centuries, multiple ships reported seeing the Flying Dutchman off the Cape of Good Hope. These weren't all drunken sailors spinning yarns. Some of the sightings came from Royal Navy vessels, with professional officers keeping formal logs. The most famous sighting occurred in 1881, when the future King George V, then a young midshipman aboard HMS Bacante, recorded seeing a phantom ship bathed in a strange red light. 13 crew members confirmed the sighting. So, what were they actually seeing? The answer is almost certainly a phenomenon called fata morgana, a type of superior mirage caused by temperature inversions over the ocean surface. When cold air sits beneath warmer air, light rays from objects beyond the horizon bend downward, creating a visual image of something that is actually below the observer's line of sight. In the waters around the Cape, these inversions are common because of the collision between the cold Benguela current and the warm Agulhas current. A ship sailing 30 or 40 miles away, well beyond the visual horizon, could appear as a floating image suspended above the water, distorted, taller, and narrower than the real ship, moving in ways that didn't correspond to normal sailing. A Fata Morgana mirage also has a peculiar quality where it seems to stay at a constant distance from the observer. As you sail toward it, the optical conditions shift and the image retreats. This perfectly matches the most common feature of Flying Dutchman sightings, a ship that could never be reached, no matter how fast you sailed. The red or glowing appearance reported in many sightings is also consistent with Fata Morgana, when the mirage bends light from a sunlit ship while the observer sits under cloud cover. The image can appear unnaturally bright or luminous. So the ghost ship was probably a real ship, just one that was too far away to see normally, brought into view by atmospheric optics and made to look supernatural by the distortion of the mirage. But there's another layer to the engineering story that makes the Flying Dutchman legend specifically Dutch. The Dutch didn't just build ships. They built an entire industrial ecosystem around shipbuilding that was centuries ahead of its time. The Zaanstreek region north of Amsterdam contained over 600 wind-powered industrial mills by the mid-1600s. These mills sawed timber, ground pigments for paint, processed hemp for rope, and manufactured the iron fittings that held ships together. The timber supply chain alone was a logistical marvel. The Netherlands has almost no native shipbuilding timber. The oak and pine needed for hulls, masts, and spars came from Scandinavia, the Baltic states, and Germany, floated down rivers to ports and shipped to Dutch yards. The VOC maintained contracts with suppliers across Northern Europe, ensuring continuous material flow. The quality control was equally sophisticated. Dutch shipwrights graded timber by density, grain pattern, and natural curvature. Oak intended for hull frames was seasoned for 2 to 3 years before use, because green timber was known to warp and crack as it dried, potentially opening seams and creating catastrophic leaks. The iron came from Sweden and the German Rhineland. Dutch blacksmiths forged bolts, nails, anchors, chain plates, and the iron knees that braced critical structural joints. A bower anchor for a large East Indiaman weighed between 2,000 and 4,000 pounds and required days of forge work to produce. The sails were made from canvas woven in Dutch and Flemish mills, strong enough to withstand 50-knot gusts, but flexible enough to be shaped and trimmed by the crew. Dutch sailmakers reinforced stress points with extra layers of canvas and leather patches, extending sail life in the brutal southern oceans. Navigation equipment represented yet another Dutch engineering specialty. By the mid-1600s, Dutch instrument makers were producing the most accurate compasses, astrolabes, and cross-staffs in Europe. The VOC also invested heavily in chart making. The company employed its own cartographers who compiled navigational data from returning captains into increasingly accurate charts of the route to the East Indies. These charts were closely guarded secrets. A VOC chart showing the safest Cape Passage was worth a fortune to competing companies. Captains were required to return their charts at the end of each voyage, and unauthorized copying was a criminal offense. The human engineering was just as important as the mechanical kind. VOC crews were organized around a strict hierarchy with specialized roles. The captain commanded. The first mate handled navigation. The bosun managed the rigging crew. The ship's carpenter handled hull repairs. The cook was responsible for keeping hundreds of men fed on a voyage that might last 2 years. And the food supply chain was its own engineering challenge. Ships carried hardtack, salted meat, dried fish, cheese, beer, and water stored in wooden casks that fouled with algae and bacteria after a few weeks at sea. Scurvy was the great killer. Caused by vitamin C deficiency, it could disable a crew within 2 months of leaving port. Symptoms began with fatigue and joint pain, progressed to bleeding gums and tooth loss, and ended with organ failure and death. On some voyages, scurvy killed more crew members than storms, accidents, and combat combined. The Dutch were among the first to recognize the connection between fresh food and scurvy prevention, though they didn't understand the biochemistry behind it. VOC ships were instructed to put into port wherever possible to take on fresh fruit and vegetables. The company established supply stations along the route specifically for this purpose, the most important being the settlement at the Cape of Good Hope itself, founded in 1652, specifically as a resupply point for ships on the East India route. The founding of Cape Town was, in a very real sense, an engineering solution to a human body problem. Dutch ships were arriving in Batavia with crews so devastated by scurvy that they couldn't unload their own cargo. The Cape settlement provided fresh water, meat, vegetables, and a hospital for sick crew members. But even with a resupply stop, the passage remained deadly. Ships were lost to storms, to fires, to groundings on poorly charted reefs, and occasionally to enemy action. When a VOC ship went down, it took its cargo with it. A single returning East Indiaman might carry 200 tons of pepper, 50 tons of cloves, bales of silk, crates of Chinese porcelain, chests of tea, and bars of tin and copper. The total value could reach 500,000 guilders or more, equivalent to tens of millions of dollars in modern currency. The loss of a loaded East Indiaman was a financial catastrophe. It happened regularly enough that the VOC became one of the earliest companies to develop sophisticated insurance schemes, spreading the risk across multiple investors. This financial engineering was as innovative, in its way, as the shipbuilding itself. And yet, ships kept going down. The Batavia, wrecked on a coral reef off Western Australia in 1629, became one of the most infamous maritime disasters in history when a mutiny and massacre followed the grounding. The Vergold Drake, or Gilt Dragon, went down off Australia in 1656 with a cargo of silver coins worth millions. The Zuidorp vanished off the Australian coast in 1712 with all hands. Each of these losses added to the aura of danger and mystery surrounding the VOC's operations, and each one reinforced the idea that the Cape Passage was a place where ships and their crews could be swallowed whole by the ocean. The Flying Dutchman legend crystallized all of these fears into a single image: a ship that tried to round the Cape and failed, a captain who refused to turn back, a vessel condemned to sail the same impossible stretch of ocean for eternity, never finding port, never finding rest. It's a ghost story, yes, But it's also a monument to the ambition and the arrogance of an engineering culture that believed it could build its way past the limits of the natural world. The Dutch built the most advanced ships in human history up to that point. They developed supply chains, navigation systems, crew management protocols, and financial instruments that anticipated modern maritime practice by centuries. And the ocean still beat them. Not every time, but often enough that the men who sailed those ships needed a way to talk about the fear. The Flying Dutchman gave them that. A way to say, without quite admitting it, that some passages are beyond the reach of even the best engineering, that some corners of the ocean belong to something older and far less forgiving than any hull or rigging system ever built. The ghost ship isn't really a ghost, it's an afterimage. The combined memory of every Dutch vessel that tried to round the Cape and didn't make it. Every captain who drove his crew too hard, every timber that cracked, every seam that opened, every mast that came down in a squall. The real Flying Dutchman isn't supernatural. It's an engineering failure at the edge of the possible, and that might be the scariest thing about it. The VOC was dissolved in 1799, bankrupted by corruption, war, and the same overreach that sank its ships. But the shipbuilding innovations it drove, the fluid hull, the standardized construction, the rigging systems, the navigational protocols, all of those lived on. They became the foundation of European naval architecture for the next 2 centuries. And somewhere off the Cape, on certain nights when the temperature inversion is just right and the Agulhas current is running hard against the swell, you can still see something on the horizon. A shape, tall masts. A narrow silhouette against the sunset. Moving, but never arriving. It's not a ghost, it's a mirage. The light bending around a ship that's really there, just too far away to reach. But if you were a Dutch sailor in 1680, exhausted, half dead from scurvy, watching your ship flex and groan in a Cape storm while your captain refused to turn back, you might call it something else. You might call it the Flying Dutchman. And you might believe, with everything you had left, that some ships were never meant to make it home.